Thank you very much, CC, for arranging this wonderful symposium. And thank you, Professor Paul Wright, for introducing me and being such a good mentor all these years. I'm going to talk about a collaborative project we have with UC San Diego. And before I get into that, I'm going to give you a little bit of an overview of what's going on with the research in UCLA in the context of the center, which our students called it SMERC, Smart Grid Energy Research Center. And I'll talk a little bit about the project and also about sort of how we're collaborating with UCSD. So, people have been arguing about what is this thing called the smart grid, and I think there's a lot of, debate. It's sort of this big elephant, and what does it really mean? To me, it means a system that is going through dramatic changes. The traditional model of the grid is large generation, and Paul talked about coal, he talked about natural gas, nuclear. Those have been sort of the big, large sources of generation, and we are moving more towards, hopefully, towards renewable. And of course, Paul pointed out what a tiny sliver of renewable we had today. But I think the next generation, and Paul had a picture of his daughter. My son is extremely green. He's, by the way, a student at Carnegie Mellon now, where Professor Paul Wright taught. But and you see the big difference that is happening with the younger generation. They're looking for a change in terms of energy and environment. And I think that, but what does it mean for the grid? What it means is, now let's try to fast forward. Let's assume that we had 20 or 30% renewable by way of solar. In Southern California, residential solar rooftops, there's a tremendous growth in that sector in terms of the energy generation mix. What would it mean if you had 20, 30% solar? Well, we all know, we are all experts in this room here. When the sun shines one moment and the next moment the cloud cover comes. And so, of course, you have shortage of energy. That's one problem. But then there are other problems as well. For instance, you'll experience locally on the distribution side, you'll experience local voltage dips. Now, the question is that a problem? Is that not a problem? We do not know that at the large scale. Yes, it is a problem at the small scale. How do you fix it? Well, maybe you can have an energy storage system. Maybe you can have the Teslas. The previous talk was about Tesla and about porous batteries. Well, it's a very, Coulombic efficiency is very important. Why? If you look at the chart that he was showing with the number of cycles, if you start using the battery in a car and you start cycling in and out to use it as an energy storage system, which, by the way, I'll talk about what we're doing in UCLA. We're doing some of that. But we are ourselves concerned about what will it do to the battery life. My family, we have, out of three drivers in my home, we have two of us have electric cars, and I'm trying to convince the third one to move electric. But and so the thing is that, but would I plug my car onto the grid? Would I help my solar system on my rooftop? I think the jury's out on that. We're concerned about the efficiency of the battery, the Coulomb efficiency with the number of cycles, and you saw as you start getting towards 1,000 cycles, you get into trouble. And so, yes, you could try to think about energy storage system, battery systems, and so on and so forth that can help the grid. So the grid is going through big changes. We are going towards solar, more renewable, at least here in California. We're going more towards wind and so on and so forth. And so then the intermittent nature of this particular generation source requires some sort of interference by way of energy storage systems to stabilize the voltage, also frequency perturbations at a local level. How do you take a battery system and use that to stabilize the frequency locally? Does it matter? Is it a big deal? Is it a big issue? How does it? And so there's a lot of issues of power quality when we start getting into 10, 20, 30% renewable intermittent resources. So there's a lot of research that still needs to be done. So 20 years from now, we have this grid, and what do we have at our disposal? We should have throttles. The throttles should be at the local level. What does a throttle do? It can take a generator like a solar rooftop and completely remove it, or it can reduce the amps flowing out of the generator by way of smart inverters. You saw the word inverter in my first slide. You should be able to change power flows. The grid will go from a unidirectional power flow to a multidirectional power flow system. So there's a lot of changes that are needed to make this grid smart in the future. Today, the grid, historically, if you think about, is our grid smart? Well, if generation is fixed and consumption is fixed, and you have large-scale generation, then you have nothing to do. But that is not the direction in which we are going. So one of the important things we are looking at in UCLA are microgrids. So we have defined UCLA as a microgrid. We make roughly 50 megawatts of power through a natural gas plant. And then now we've started adding solar. We have a small solar installation, about 50 kilowatts, adding another 100 kilowatts early next year. So we'll see, hopefully, the solar mix increase in our microgrid. The other 20 megawatts we buy from the city of LA. So we're like a little town that consumes at peak 70 megawatts of power. And within that, we are able to experiment with things. So we have a very interesting sort of a research infrastructure. In the concept of the microgrid that we have, of course, we look at forecast analysis. We look at forecast. We use that for data analysis. There's the energy demand response, energy scheduling, the optimization, and of course the human interface, by way of visualization and mobile apps. This is just just an overview of our research. Now let's look at the UCLA's infrastructure and what's going on there. What are we trying to do within the microgrid? So if you look at these three arrows, information, power, and control, the traditional model of the grid is all three of them are pointing in the same direction. A smart grid, to me, implies that power flows, information flow, as well as control flow are both bidirectional. Meaning what? Meaning I should be able to go buy a solar panel from Best Buy, plug it in, hit a button, and it should work as a plug-and-play device, like a consumer device. It should inform the utility that I'm now a generator. And I love this word called prosumer. In Southern California, our utilities are using this word prosumer. What it means is that the individual user is not just a consumer of energy, we're also a producer of energy. That means that you need significant communication, so WAN, LAN, NAN, MANs, HANs. These are all different types. We all are experts here. We all, in wireless and wireline communications. And we go from unidirectional power flow, control flow, and information flow to bidirectional. So there's a lot of research needed. So now I'm going to jump to the electric vehicles, which is sort of the topic at hand. And so in UCLA, one of the sort of the research paradigms we have is, if you want to have electric vehicles, and if you rewind backwards many years, over half a decade ago when the first EVs were coming online in LA, I talked to the local facilities manager, and they said that, at that time the EVs were running at 3.3 kilowatts. Today they're around roughly 6.6 kilowatts. Soon they'll be at 10. At 10 kilowatts, if you have 1,000 cars, and if UCLA is a 70 megawatt shop, right? At 1,000 cars, which is less than 5% of all the cars being EVs, we're already in trouble. Okay, you have 10 megawatts of load. So the question is, what do you do if you don't do that? And can you, instead of the EVs being a load, can you aggregate them? Can you manage them to be able to put them to use, as opposed to them being a burden on the grid? For instance, charge at night or charge during times when you don't have the peaks. And so essentially an information-based system has been created to allow us to test different types of concepts on campus. And we have, there's a control center to which all the information flows. And there are some interesting energy management approaches that are adopted at the charging station level, and at the oops, I guess I can't go back up here, but then never mind. At the charging station level in the garage, at the control center on the cloud, as well as at the user operator level. One of the things, let me just bring this. Okay, yeah. So this particular chart, it shows you that there is no vehicle charging. Then one person plugs in the car. So this is an intelligent circuit. What it does is it does multiplexing of energy, so that if you've decided that at this time of the day, the maximum consumption I'm going to have is this many kilowatts, then if you have n vehicles, it tries to split up that energy consumption over n vehicles. And why does it do that? Well, think about it. If you have electric vehicles that are parked all day, and you have enough time, well, why not utilize that time and multiplex the same circuit into multiple vehicles? And again, why would you do that? Because the cost of infrastructure is substantial. So if you want a smart grid, instead of adding massive capacity, utilize algorithms and software to distribute energy at the local level. So this sort of a notion can be adopted, at the distribution level, at the garage level, and at the car level. So the idea is that things are controlled by algorithms and by software, and things can be smart, and you don't sort of bother the user with specifics. So EV aggregation is another very interesting, I think, research opportunity. And one of the things we're trying to do is, if the grid operator, so we work with the City of Los Angeles Department of Water and Power. We were fortunate enough to be part of their $120 million smart grid demonstration grant with USC, as well as JPL Caltech. And one of the research issues that we're looking at, that we have been looking at, and of course that carries into this project as well, maybe we're able to utilize that infrastructure in our CEC grant, which is to look at what a load requirement in a distribution circuit is. So if you have the load requirement in a distribution circuit, then the question is, can you take the personal preferences of individual EV drivers and fit into that load requirement on that distribution circuit? Why is it important? Why is distribution circuit important? Well, if you look at what's going on in California, our population continues to grow. And if, you know, smart grid, to me, another aspect of smart grid is about management of resources in a more efficient manner, as opposed to adding more capacity. This just shows you a bunch of parking lots in UCLA. These are this is a level 1 charger. That's essentially a 110-volt charger. That's a level 2 charger. It's a 220-volt charger. So this is a technology that came out of a couple of PhD theses. And essentially this particular student and our research team has installed to date 212 electric vehicle charging stations in and around UCLA. We have over 100 EV charging stations on campus for our research test bed. And so it's a rather significant undertaking, and we're very fortunate that we have support of the local utility and also 2 cities, Santa Monica and the city of Pasadena. So we have installations sort of not just in UCLA, you know, a little bit beyond UCLA as well. And then you have this thing as a level 3 charger. A level 3 charger is a 50 kilowatt system. Okay, so now it's, you know, if for those of you in the battery space, I mean, you're probably thinking, oh my God, this is going to kill the battery. Darn right, you're darn right. It's going to kill the battery. And if you take a Nissan Leaf and charge it 90 days in a row on this charger, you're doing tremendous damage to the battery. So people are talking about innovation being, how do I pump large amounts of energy into a battery? No. How do you manage the total energy portfolio that you have? I think that's the bigger research issue, given the constraints of the battery. So for instance, if you pump 50 kilowatts into the battery once, well, the next N chargers, you should only pump 6 or 7 kilowatts. So level 3 chargers, you know, are a great opportunity. So what are we doing there research-wise? We are attaching used car batteries to that charger, so that instead of putting the 50 kilowatts as a load on the grid, we only put 25 kilowatts on the grid, and the other 25 kilowatts comes from the battery, based on the statistical assumption that there is a sort of a gap in the usage through the day. And of course, your battery size can vary depending on the gap you have. So that's another interesting. So now sort of jumping into our research project here, the title of that is Control of Networked Electric Vehicles to Enable a Smart Grid with Renewable Resources. So this essentially, again, sort of the research here that we're trying to do is about the 3 layers of communication, computing, and control that talk to the physical layer. And we're looking at a situation where you have electric vehicles and solar combined, and again, within the UCLA campus setting so far. And you know, the research infrastructure is in the distribution network, and we're looking at data flows, power flows, and then combined data and power flows, and then the multiplexing capabilities really down at the individual level. So the question becomes, what sort of research infrastructure is needed, and how do you model, and how do you actually control this kind of an infrastructure in the context such as the solar you know, fluctuation that I talked about. This is the V2G research test bed. This is a Mitsubishi IMEV, and this is essentially we use what's called the DC. It's essentially a DC port, the Sharama port on the Mitsubishi. So we go DC to AC, and then we have to rectify that AC. And what are we trying to do? We're trying to do what's called vehicle to grid. What is that? That has to do with taking energy from the car, sending it back to the grid. It's a simple thing. Conceptually, it's simple, but then From a practical standpoint, you have to get the buy-in of the user, you have to look at the damage to the battery, and so on. And when does the grid actually need this power? That means that there needs to be a method to send a demand response signal to a car. So that means, I go back to the previous slide I talked about, there's a communications piece, and there's a control piece. So all of that goes into this, and that system has been developed by one of our PhD students. So here you see on that particular hardware, you see a desired curve for the V2G, i.e. sending power back to the grid when the grid needs it. And essentially it shows you that this is the ideal desired curve, and then this is sort of in different situations, this is sort of what we actually have measured. That just shows you some of the different, the different layers we have, and essentially from the lower layers are the hardware layers, and the upper layers are the software layers, and eventually it's all connected to the internet. The other part of the research is, if you, again, try to connect this kind of infrastructure to the grid, you need to be cognizant of research standards. The utilities are very much interested in this standard called the IEC 61850. And it's a very complicated standard if anybody's interested in that. But what it allows you to do is it allows you to take your physical infrastructure, put it in one place, and then remotely through different protocols, you can talk to what's called a client. A client can be a mobile app or a web service or anything like that. It's just a software interface. And one of the things that we've been doing on this is we're actually collaborating with Korea Institute for Energy Research for many years, whereby they have the hardware on their end, we have the algorithm sitting here. And you'd argue, well, yeah, there's delays in the communications. Yeah, but that's all part of the research. Not everything requires sub-microsecond controls. Some things have a 15-minute delay, some have a 1-minute delay. So the thing is that you have to look at the requirement to find a solution. So you have to really identify and define the requirements when you're connecting these devices to the grid. So we're doing two pieces. The first piece is simulation. So we actually have a IC client gateway simulation in our lab. And so what we do is we actually run the simulations first to see how a particular device would behave when you connect it to the grid using the IEC 61850 gateway. So it simulates the gateway itself. And then you connect different devices on one end of the gateway, and then you see how the gateway and the client talk to each other. Now, we've published a paper on this one as well, connecting it to a vehicle-to-grid system. The research challenges here have to do with overheads that are associated with standards. I think at some level, I think that some of the standards that sort of get out there, I think that they're too big and they may not work for all the different research needs that you may have. So I think you have to really look at the standards very carefully. And I think before anybody embarks on 61850, please talk to my PhD student. It's a very large and it's a very complicated standard. The other piece of the research that we've been working on is using a mobile app to take historical data, to have user interaction, to have pricing information, to take, then you come up with what's called a bidding policy that allows people to bid different amounts for the energy. For instance, on that multiplexing chart that I showed you, when two cars need energy, what do we do in that garage? We split the energy between the two vehicles. However, if one person says, I'm willing to bid more, so we actually have a PhD student who's built an app. I'd be glad to show you. So this is an actual screen dump of that app. And here you bid in a price. And what we do is we pull real-time CalISO pricing. We take the CalISO pricing, and we add a retail factor to that the local operator would add. And then you enter your threshold pricing. Now, if you're below the CalISO pricing, then you're sort of out of luck. You're not going to get any energy. If you're above, then you get the energy, but you split it with what others are bidding. So this is a very interesting research experiment. We have data for 3 months. If anybody's interested in working with us, we would love to have economists play with this data. We're not economists where this was something our students were having fun, and then they just started building this, and they went and built this. And we have this implemented in 3 parking garages on a daily basis. And people, people, I think, they get very upset when they see this kind of stuff. But We've had a lot of complaints about this. Oh, I didn't get any energy today. Well, did you look at what the pricing was? Why are you playing in this charging station, right? You can go somewhere else. But in any case, so there's an interesting research that our PhD student Bin Wang has published a paper, and he's working on additional publications. We collaborate with UCSD. So yes, Southern California does exist, and we have also Professor T.C. Sauer, chairman, is also going to be speaking later today from UCLA. And so we collaborate with Professor Rajesh Gupta from UCSD, and his research team, I believe, is here today. And but in the interest of time, I'll just say a couple of words about their team. So I believe Balakrishnan is here. Balakrishnan, can you raise your hand, please? Can you just stand up and wave to everyone? Thank you very much. He's our wonderful collaborator from UCSD. And we have Muhammad, who's a student, and Dr. Rajesh Gupta had to be in Washington for something else, so he couldn't come. But overall, they're looking at a couple of important problems. So one is they're looking at what's called workload deferral and dynamic storage capacity in EVs to mitigate the variability in renewable power generation. So what they'll do is they'll look at the curves that look like this, and then and again, their work is on the simulation and the modeling side, and they're able to take sort of these power curves and smoothen them out, because if you look at this sort of variability in the solar, right? I mean, that's sort of the thing that we don't want. That's the intermittency that we don't want. So they actually have models to solve that problem, and I'm sure he can answer questions more detailed. The second issue that they're looking at is peaks and valleys, which nobody wants, and everybody wants a flat curve. So how much of a peak and how much of a value can you cut off by having a battery for energy storage? So they're looking at that as sort of the second problem. And again, I'm not going to go into details. I'm out of time here. Time's up, and my presentation is up. Thank you very much.
Thank you. Any questions?
So, Daniel Estrada from UCSD. Yeah. You were mentioning that some people would go into these garages and then not get any energy because they didn't bid enough.
Yeah.
Could you see a system where you kind of can put in, all right, I want to charge this much, try to make it as cheap as possible by charging at the right times? Is that something that, because I'm pretty sure San Diego Gas and Electric is working with that, where you just say, like, cheap charging and...
Yeah, so I didn't have time to get into the details, but you can define, so we actually have a bunch of apps in different garages that we're trying out. So I just showed you an example of one of the apps. So you could either define your requirement based on the pricing, or you can define it based on, and in fact, if you do that, we will tell you that by 5 p.m., and if you tell us, there's another part of my screen there that asks you, how many miles do you want today? And we'll tell you that by this much time you'll get that many miles. Or you can say, I want to leave by 5 p.m., and we'll tell you, based on what you have said, based on the past projections, you're going to get so many miles by 5 p.m. So yeah, we have that. So you trade, essentially the trade-off is, which you correctly pointed out, is there is time, there's money, and there's amount of energy.
I apologize if I wasn't here earlier. I'm Mark Madera from UC Davis. But it's not got to do with my job. I own a Tesla, and I noticed that it charges at up to 130 kilowatts. And that seems like much higher than what you're talking about. And they have these charging stations, a whole bank of them. How is that being dealt with at the grid level? And then B, at those charging rates, I'm assuming they're doing damage to my battery, but I'm guessing that my warranties, if I eat the battery before my warranty's up, they'll give me a new one.
Yeah, so Tesla is a rather interesting. So we have experimented with over 30 EV models, and we've experimented with the Model S very extensively. We have a bunch of them on campus. And Tesla, because, I mean, and they have a non-standard interface. So first of all, our experiments with trying to make EV charging in Tesla grid friendly, and like I said, we needed a throttle to throttle back and up. And it's been a challenge because of the way Tesla deals with things. And one of the things Tesla does, by the way, so that you know, is if we throttle 5 times, after the 5th charge, we've discovered in the last month or so, after the 5th cycle, Tesla then blocks our charger. We have to take it out and put it back again. So if you're thinking of it sitting on the grid, And so but these are practical things they do because they're concerned that there's a problem in the power quality on the grid. So they'll do that. But coming back to your Tesla question, 120 kilowatts, yeah, I wouldn't do it. I would not do it at all on a regular basis. And so that's a very, very heavy load on a battery. And again, we have the battery expert right here, but I'm sure he'll tell you that you want to minimize the kilowatts going in. So what we do in our research is, if you say you're going to be here till 5 p.m., we actually reduce the kilowatts and the amps going into your car, so that it's better for it's better for the battery and better for the grid, and better for the distribution system, better for the garage. You have less capacity requirements, and this is how we are able to take a single circuit. And the charging station that I showed you actually has 4 outlets. So we have what's called a quad multiplexer. So we found in an 8-hour day, for a typical driver of a typical car, I can on a single circuit charge 4 cars.
But with that argument, you'll never go to having electric vehicles replace gas vehicles for long distance travel.
No. See, again, your question was, should I charge at 120 kilowatts every day? Don't do it every day. But if you did once in a while, it's okay, right? I mean, once in a while you eat lots of stuff with greasy fat burgers and stuff, and but you don't do it every day. It's the same thing. Yes.
Hi, I'm Shing from San Diego State. I'm just wondering, do you have an idea how many people are participating in those bidding games you have on campus? Like roughly how many people are participating?
Yeah, I can tell you, basically on campus you have to set up an account with our system, and so we have roughly maybe about 20 EV drivers. If you need more specific data, we can give you more data on that. We'd love for somebody to analyze it, and
Maybe one more question.
I think actually we should go to a break.